Okay, next question, question 6. Analyze ADC result. So we have this 10-bit ADC. I think if you refer to the module, if you get the formula and press. So basically this one's still in our chapter 2. So remember all of these will my tested in your final exam as well. Okay, directly or indirectly. So this one basically is the table 2.4. Okay, so you have seen the formula. So basically this one slightly reverse a little bit. So we have a V reference 3.3 volt. The example is 5 volt. Okay, and after that, so you can also be the V out. Okay, divide by the V reference. Okay, and then we multiply to the 10 bit. 10 bit is a 1023. Okay, how to get this 1023? So basically you need to using the 2 to power 10. Okay, so basically it's a 1024. It's not 1023. Okay, so because it start from 0, so basically we should use it 1024. So it start with 0, then we divide into 1024. So what is this? But we need to minus 1, so still a 1023. Okay, so next is the reading. Okay, 512. So basically you can make it like this. Okay, so this is a formula. So basically the left hand side is a voltage, the right hand side is a digital. Okay, so the maximum 1023. Okay, so this is a maximum. So the voltage for the pin is according to the V reference 3.3 volt. Okay, so after substitute 3.3 volt. Okay, then you will get the VL equal to what? Equal to whatever at your right hand side multiply to 3.3. Okay, so using your calculator, that we get the answer is A. Okay, 1.6516. Okay, so that means the question it can asking you anything. Maybe ask you what's the V reference, what's our example in the module 2.4. 2.4 is about the ADC output. Okay, so that's why if they ask telling you 1.65 we measure, so what is the digital ADC value? So it will be 512. Okay, so that's why you need to be totally understand what you are doing. Okay, next, push button is connected to pin D4 with an external pull down resistor. Analyze the logic step of D4 when the button is connected to 5 volt is pressed. Okay, push button is connected to D4. Okay, connected to D4 and external pull down. So it is using the pull down. So what it means using a pull down? So the pin will always go to low if nobody activate it. So it's active high. Okay, analyze the logic gate of this pin. Okay, when it's pressed. So when it pressed, it's active high. So the answer is definitely the A. Okay, high impedance. A high impedance because they analyze the logic gate. So high impedance is, we cannot say wrong, but the question is analyze the logic state of D4. So the answer still maintain the A. So logic gate, logic state only high, floating or low. So answer is A. It's very straightforward. Okay, engineer using the SPI over I2C for a high-speed display application. Analyze the primary technical justification for this choice. So why using the SPI? SPI, what is this? It has a more pin, am I correct? So it allow multi-masters or a send bus easily. I2C only have one master, but SPI have multi-master. This one unclear. So let's move on. Full duplex, I think this one is correct. Okay, because I2C is a half duplex. It only have one data line. Okay, when you from master to slave, you can know from slave to master. Okay, so full duplex that means master input, slave output, and also the master input, slave, master output, slave input, master input, slave output. Okay, it can be run at the same time. So this is a full duplex. Support much higher clock speed without RC delay or pull out. Okay, RC delay or pull out, this one definitely is I2C thing. I2C have a pull out. So look like its answer is B. But let's continue, don't just stop here. SPI using fewer wire, this one is wrong definitely because it have more wire. So if you your design is only need less, need fewer wires, so should be using the I2C instead of the SPI. Okay, SPI have a built-in error checking. This one is not the error checking. Okay, this one is wrong. So this one is a chip selection. Okay, so that's why it's wrong. So that's why the only possible answer is B. Okay, so next, the number 9. Which of following is incorrect characteristic of hard real-time systemation chapter 1? The system must provide guarantee worst case response time. Must must guarantee worst case response time. This one, okay. This one okay. We are looking for incorrect. Okay, timing correctness is as important as logical correctness. Okay, so this one we also cannot say wrong. Okay, so next, missing a deadline is acceptable. This one definitely wrong. Okay, because it's a hard real time. So failure to meet constraint can lead catastrophic consequences. This one also very definitely the answer is correct. That's why the answer for incorrect is C. Okay, this one answer is C. Okay, so next, yeah. Question 10. Analyze the following scenario. A flight control system with a commercial aircraft must adjust the wing flaps every 10 milliseconds. Okay, so this is the logical correctness and also the temporal correctness on it because there's a time. If a computation time take 12 milliseconds due to the system glitch, the aircraft lost stability. Classify the system lost stability. So definitely is what? Real. Which one? Lost stability. Can function or look like still can function, right? Okay. Or cannot function. Already lost stability. Look like fail already, right? Because the stability is very important. Okay. So if they say the aircraft still maintain acceptable ability, that it can be a firm. Okay, soft meaning that it still can maintain. This one firm meaning that it can maintain acceptable stability. So but now it lost stability already. So that's mean it's going to crash already. So that's why it's a hard real time. Okay, so this one this question also quite straightforward. So okay, next, because the computation time take longer, so that's why it missed the deadline. So that's why hard real time system. Okay, next, which of the following best describe temporal correctness in embedded system application? So the clock speed is running maximum rate. This one is definitely wrong. So the temporal correctness, that means we want to make sure the timing constraint has been fulfilled. Okay, by adjusting or by scheduling the task accordingly. So the system use the real-time operating system like FreeRTOS. This one, no that best description. No best. Let's continue to read. The mathematical result of the task is calculated without any round. This one also something not so sure what they're talking about. The output of a task is produced within specific defined time constraint. Time constraint. Okay, so this one I think is correct. So output must be delivered within the specifically defined time. So just now this one, we actually we end every 10 milliseconds. So it should be fulfill this one. Okay, if not fulfill that, it depends if hard real time system that the system lost already. Am I correct? So that's why the answer look like definitely is D. Okay. So next 12. An online video game experience lag. Okay, where a player's action is delayed 200 milliseconds. So there's a delay 200 milliseconds. The game maintain playable. Okay, still can play but experience declare. So what is this? Example of soft real-time system, because they're not given the what the firm real-time system. Logical correctness fail. Actually, it's no fail. Okay, because it's still playable, so that means still can play. Just the experience that you know no good. Predictable determination also no. Hard real time definitely no. If hard real time it missed a little bit, that it should be fail already. So the only answer here is soft real time system. So next, determine the incorrect statement regarding predictability in real-time embedded system. Incorrect. Okay, which one incorrect? Predictability allow an engineer to guarantee that a deadline will be met. Actually, as an engineer, you cannot guarantee something. Okay, so this one we post first. This one I think is not it's not wrong or not correct. It's not so clear. Okay, so predictability allow an engineer to guarantee a deadline will be made. Okay. Okay. So next, a system with a high jitter is considered to have low predictability. So this one also know that correct or also know that incorrect. Okay. So if your jitter is high, so yeah, actually the predictability is I mean the deviation is very big. If it says low predictability, still look like still acceptable. Okay, still you cannot say wrong. Okay, predictability means the systems always run at the higher possible speed. This one definitely is wrong. Okay, why? So since we have select the incorrect answer, so this is an incorrect answer. So it doesn't mean it must be run highest possible speed. So the one is wrong. Okay, as long as if you well schedule the task accordingly, that it should be can be a predictor. Okay, so the last one, the predictability is essential for the hard real-time system. This one definitely. So the answer is C. Okay, next is about the microwave oven use an embedded controller to control the heating process. When the timer reach 0, how would this be classified compared to a pacemaking hub implant? Pacemaking hub implant. Okay, so pacemaking hub implant I think is a hub real-time system, correct? Compared to the oven. Oven is a commercial device, microwave oven. So both have a controller definitely, but for one is slightly, I mean definitely is very relatively cheaper compared to the medical grade device. So let's go through the selection. Microwave is a hard real time, wrong. Okay, it's definitely wrong. Both hard real time also wrong. If we make our microwave oven become a hard real time, it will be very expensive. So this definitely don't have that what we call requirement to make the oven as a hard real-time system. It basically make your problem very, very expensive. Okay, and then the company bankrupt definitely. So that's why the best way is microwave, soft, and then this is the hard because it involves a human life. Okay, this one is just a piece of a cake, piece of a milk. They're going to cook it. Okay, so that's why the best answer is C. So either one are real-time system, this one also wrong. Okay, basically all commercial system are real-time system. Okay, either soft or hard real-time system. Okay, last question. An autonomous vehicle's radar sensor processes data every 15 milliseconds. If the logic correctly identify an obstacle, but the signal reach the braking actuator at 55 milliseconds, resulting in corruption. Okay, so that means that the system not fast enough. Okay, because it processed that this, and then the signal reach the braking is too slow already. So that's why when you have this design to refine the design, okay, so that it can effectively minimize the corruption. What type of failure that occur? Right, process data every 15 milliseconds. So the logic correctly identify an obstacle, but the signal reach the brake actuator at 55. Okay. Look like it. Okay. Let's see. Soft real-time failure. Firm real-time failure, logical failure, or temporal correct. Temporal failure. What is the temporal failure? So which one? So basically, we back to the definition of soft real-time system. Soft real-time system meaning that if it missed the deadline, that everything still okay, acceptable, correct? So this one acceptable now. Look like not acceptable, correct? Because the corruption happened. Okay, the accident happened. So meaning that miss the deadline, corruption happened. Okay. So look like this is no the failure of the soft real-time system. Okay, this one wrong. Firm is slightly same as a soft. So also not applicable today because it missed a deadline that corruption happened. So basically the situation show that missed the deadline and the catastrophe happened. So that's why this is a hard real-time system. Logical failure, no. Okay. So basically logical fail, no. Look like no fail, correct? Because it is somehow it detect the obstacle and then send a signal to the actuator. So that's why this one also no failure. Okay. So look like logical is okay, but the temporal failure. So that's why the answer is D for this case. Okay. So basically this is the discussion for our quiz.